Well, let's take that information learned from the previous lesson on half-parabolic trajectories and try to put it into practice. So here's an example problem. It describes somebody who drives a pickup truck off the edge of a cliff. So they failed to notice that the bridge is out, unfortunate, and they're traveling at 20 meters per second when they approach a canyon, and as a result, the vehicle flies horizontally off a 78-meter tall cliff. Part A, how much time does this person spend in free fall before impacting the ground below? Now, before I get too far, I need to take my own advice. We always spend more time setting up a problem than we do solving the problem. So I don't want to try to do any number crunching until I've represented this word problem in a graphic manner. And this just helps when you revisit your work, or if you're trying to share your work with other classmates, that you can take in the information in one quick view and progress quickly. So, pickup truck. Traveling 20 meters per second. Goes right off a cliff that's 78 meters tall. We know the shape of the path will be half of a parabola, and we have to determine how much time is spent. We also have to figure out what's the range of the projectile. So we can put this in here now. R equals question mark, T question mark. Ooh, we're also asked the angle of impact. Okay, so if we make a line that's tangent to the parabola at the point of impact, and it's expressed about at that angle right there. So theta is also a question. And finally, what's the magnitude of the total velocity, which is really like asking, what would the length of this vector be? What's the value of the speed, right? The magnitude of the velocity can be interpreted as the speed. If you give the magnitude and the direction, then you're giving all the information about velocity. So we really will have all the information about velocity because we'll give the magnitude and we'll have solved for the angle. So let's take it one step at a time, figure out what's the time of flight. So from the previous lesson, I'll remind you where this equation comes from, but you might know that you can just jump to t equals the square root of 2h over g. Now, let me label these. When I say 78 meters, I can identify that with the symbol h, and when I say 20 meters per second, I can identify that with the symbol v0. Maybe we'll even call it v0 subscript x to remind ourselves it's only applied in the horizontal direction. Now, where did this come from? It comes from delta y equals v0 yt plus 1/2 gt squared. There is an initial velocity of 20 meters per second, but not in the vertical direction. And instead of calling it delta y, we call it h. So it's just a matter of simple algebra to rearrange that equation. So if you want to do some number crunching with me, grab your calculator. We're going to take the square root of 2 times 78 meters and divide that by 9.8 meters per second squared. Dimensionally, the meters cancel out, and we know the units are going to be seconds. So that's good that that works out. 2 times 78 divided by 9.8 gives you about 15.9. When we take the square root, it rounds up to be very close to 4 seconds. So we can either report this as 3.99 seconds if that makes you feel good, or if you don't mind rounding up, we'll round it up to 4.0 seconds. Okay. Let's figure out the range. So the range of the projectile is governed by the equation delta x, right? The range is a horizontal projection equals initial velocity times time plus 1/2 at squared. There is an acceleration of 9.8 meters per second squared directed downward, but there is no acceleration along the x-axis, so this term disappears. So this is just distance equals rate times time. So our range is equal to v0 x times t, but we just found that t is the square root of 2h over g. So we're really just multiplying 20 meters per second times 4 seconds. Give us 80 meters. All right, moving on. Let's find the angle of impact. Now let me show you one of the common mistakes I see in problems of this type. we know we're going to have to take an inverse tangent, right? The tangent of an angle is equal to opposite over adjacent. So I've seen solutions that attempt to take an inverse tangent but using the wrong information. Okay, so the path taken is a parabola. Oh, I didn't get that angle very good, did I? Let's redo this. So the path taken is parabolic. The angle is an extension of whatever the tangent line would be at the end of that half parabola. And so we're going to take the inverse tangent of, let's see, this is 78 meters, isn't it? And this is 80 meters. So the mistake I see is thinking that you can use alternate interior angles and say, well, if that's theta, then that's theta, and then opposite is 78. So theta must be the inverse tangent of 78 over 80. No, that would be if the projectile didn't follow a parabola, but followed a path that was like this, right? We know this isn't the case. This is going to sound more like cartoon physics than real life physics, right? So a truck's zipping along the edge of this cliff, flies off, and then just goes straight down in a straight line. But that's not the path taken at all. So we need to take an inverse tangent, but not of the ratio of distances. We need to use the velocity vector in calculating inverse tangent. So we can picture a right triangle by imagining the components to the overall velocity. So if this represents the velocity, then the vertical arrow represents just the y component to that velocity. And I can use a different color. This red vector represents the horizontal component, which we know remained constant throughout the entire flight. So if it was going 20 meters per second as it left the edge of the cliff, it was attempting to travel sideways at 20 meters per second just before it made impact with the ground. So here's a right triangle. And that angle theta is the same as this angle theta. So opposite that angle is the vertical velocity, and adjacent to that angle is the horizontal velocity. So if we take the tangent theta, should be equal to the vertical speed divided by the horizontal speed. So theta is the inverse tangent of that ratio. Well, the vertical speed of impact is the square root of 2gh, and the horizontal speed of impact is whatever it was initially. So let's calculate this square root of 2gh. The square root of 2 times 9.8 meters per second squared times 78 meters. Okay, so meters and meters multiply together and give us meters squared, and the square root of meters squared per second squared is, of course, meters per second. This is good. This is good. The units are working out. So grab a calculator and play along at home. 2 times 9.8 times 78 gives you about 1,529. We take the square root of that and get about 39.1 meters per second. Okay, so our angle of impact is the inverse tangent of 39.1 meters per second divided by 20 meters per second. And according to my calculator, that's just about 63 degrees. Have we answered everything? Oh, what's the magnitude of the truck's overall velocity at impact? What's this total speed at an angle? So if we're following this idea of the overall speed representing the hypotenuse of a right triangle, we use the Pythagorean theorem, and the total speed is just the initial horizontal speed squared plus the vertical speed at impact squared. So this is the square root of 20 squared plus 39 point, is that the answer, 39.1? Yeah, 39.1 squared. And we get 43.9 meters per second. Okay, so there's a lot you can determine just based on knowing the height and the speed that a projectile flies off the edge of a cliff or a tabletop or any type of ledge such that it's projected horizontally. Let's do one more problem and we'll wrap it up. What if an object did the same sort of thing? It travels off a ledge, and this time we know it spends 1.5 seconds in the air, and the other bit of information, we know it makes a 60-degree angle of impact. Now, in this case, we have to solve for the height and the initial speed. So the picture looks the same. It's still some projectile traveling horizontally, tracing out a trajectory in the shape of half of a parabola, but this time we're given different information and asked for the height as one of our questions, and the initial speed is the other question. So exactly the opposite of the previous problem. Instead of being given height and speed and determining the angle, we're given the angle and we're asked for the speed and the height. We were given one more piece of information too. The time is 1.5 seconds. So we've got an angle of 60 degrees. And let's see if we can figure this one out. Well, if we know the time, that alone will tell us the height. So if time is the square root of 2h over g, it follows that h is equal to 1/2 gt squared. So the height of this cliff is 1/2 times 9.8 meters per second squared times 1.5 seconds quantity squared. So if the seconds get squared along with the number 1.5, they'll cancel the seconds squared with the 9.8 meters per second squared measurement. Grab a calculator, see what you get. So I come up with a height of very nearly 11 meters, 11.025. We'll just round it off to 11. Now, what about determining the speed? Well, back to this notion of picturing just the components of the overall velocity. Let's zoom in on this a little bit. So what we have is an overall speed at impact suggested by the arrow pointing at an angle. And that's a result of having a combination of horizontal motion and simultaneously vertical motion. If we use the parallelogram method, and we see two right triangles to choose from, whichever one makes sense for you. Let's just look at this right triangle. So we've got the angle. We're trying to find this side that would represent the horizontal velocity. We should be able to figure out this side right here, okay? That's the vertical velocity at impact. And that should be equal to the initial vertical velocity plus acceleration due to gravity multiplied by time. So the initial vertical velocity is 0, so that just means we need to multiply 9.8 times 1.5. 9.8 meters per second squared times 1.5 seconds, and that gives us a value of 14.7 meters per second. So the tangent of 60 degrees has to be equal to opposite over adjacent. It has to be equal to 14.7 meters per second divided by the quantity we're looking for. So we just do some cross-multiplying, right? That means the initial velocity in the horizontal direction is equal to 14.7 meters per second divided by the tangent of 60 degrees. And we get an initial velocity of about 8.5 meters per second. So I guess the point is, we don't have to always approach the problem the same way. It's not always going to be an exercise of being given the height and the speed and then trying to determine time, range, and angle, as long as you're given probably any two of those quantities. So when it comes to these half-parabolic trajectories, there's a few things to be interested in. Height, initial horizontal speed that it's projected at, time of flight, the range, the angle of impact. And I would guess that if you're given any two of those quantities, you could solve for the other three. Okay, so in our next lesson, we'll investigate projectiles launched in full parabolic trajectories. Thanks for tuning in.